Good morning. This is the session CloudHPC 3. My name is Dennis Gannon. I'm the chair of this session. And we have three very good speakers in the session. And they are right here. The first talk is by Deborah Goldfarb of Amazon. And she's going to talk about grand challenges for humanity, cloud scale impact and opportunities. And then we have Mr. Prabhat from Microsoft Azure, enabling AI at scale on science, and Jayan from UK, and he's going to talk about benchmarking for AI for science in the cloud, challenges and opportunities. So the first talk is a video that Deborah has prepared, and she will be joining us later to answer questions and to discuss it. And so I will, at that time, I'm come in and okay. Now I'm going to start there. Okay, I'm going to start the video. Now. All right, here we go. This is Grand Challenges, Deborah Goldfarb.
Hi, I'm Deborah Goldfarb, and I'm the Director of HPC Products and Strategy at AWS. We are at an unprecedented time in human history where the pace of innovation and technology are fundamentally changing just about everything we do, the way we live, the way we work, the way we interact with each other. Everything is changing, and yet the gap between rich and poor continues to grow. And as we've seen, human suffering is at an unprecedented scale. And so, what I'd like to talk to you about is just that. How do we consider the biggest problems facing humanity? And where does HPC play a role in solving and mitigating some of that suffering? So, what we're going to talk today about is data to start. Where are we? What does the world look like? We're going to talk a bit about pandemics and disease and where HPC fits into that and what we've learned from COVID-19 with some of the work we've done. We're going to take a look at what cloud brings to the story. How does it change the equation of really attacking some of the hardest problems we face? And then we'll conclude with some final thoughts. So let's take a look at some of the facts. Globally, nearly 1 in 9 people are undernourished. That's about 900 million people, and it's increasing. And after 20 years of decline, infant mortality and malnutrition are on the rise. This is just extraordinary that we had gotten it down to a level, year after decade, and here we are back up with children suffering because they don't have enough food to eat. 10% of the world's population earns less than $1.90 a day. It's an extraordinary piece of data. These people lack access to clean water and basic health care. Around 16,000 children under the age of 5 die every day, mainly from preventable causes, and a very significant portion is due to diarrhea or waterborne diseases. There's just no clean water. So children are sick and they're dying. By 2050, the population will grow to nearly 10 billion people. And we have to begin to think differently about how do we feed? How do we sustain this population? Right? How do we think about food security with 10 billion people? 71 million people around the world have been forced from their homes. Nearly 26 million are refugees, which is up 65% from a decade ago. An estimated 10 million people are stateless, with no nationality or access to basic rights such as education, healthcare, employment, and freedom of movement. And as we know now from our experience with COVID, a pathogen can travel from a remote village to major cities on all continents in 36 hours. Humanity is linked in critical ways. Globalization has changed everything around us. And yet the inequities are just absolutely extraordinary. And they're getting worse day by day. So when you think about this in the context of these humanitarian crises, we really need to face the fact that not only are humanitarian crises just horrifying in terms of the human suffering, they are also global security crises. They are destabilizing in every way when you have people who are sick, displaced, and hungry. So you have to begin to pose a bunch of different questions on what we do about it. The velocity by which infectious disease and pandemics are spread is supercharged as a result of climate change and globalization. We are changing full ecosystems because of climate change. These pathogens change their behavior. They jump to different hosts, human hosts, as we're seeing. And how do we manage all of that, as well as manage simultaneously eradicate terrible diseases such as malaria and TB and HIV? How do you balance these dynamics? Food riots have toppled governments. We've seen that. And with population growth currently exceeding our ability to produce and equitably distribute food, what is our path to food security? This is a fundamentally destabilizing dynamic. When people are hungry, they respond, and they respond intensely. And last but certainly not least, global policy regarding human displacement is fundamentally inadequate. And with the number of dislocated people growing 65% over the past decade, what does our world look like when every 2 seconds, one person is forcibly displaced as a result of conflict or persecution? What do we do about these? And where can we use technologies such as HPC and AI to begin to reimagine how you might solve some of these problems? So let's turn now to pandemics. I gave a talk using this simulation at Supercomputing in 2018. At the time, of course, this was pre-COVID, and it was 101 years since the Spanish flu. And at that time, there was a lot of epidemiologists who were building models about what would a global flu pandemic look like today based upon the same conditions that we saw with the Spanish flu, which in retrospect, the mitigation capabilities were not significant. They didn't have the technology to sequence the genome of the flu. They didn't have the technology to quickly build a vaccine, etc. But there was a suspicion that if you had a new influenza virus, such as the one in 1918, it could kill 30 million people within 6 months. And if you take a look at this video, this was the simulation that epidemiologists and virologists were using to look at the diffusion of this flu based upon the conditions that existed at the time of the Spanish flu. Well, certainly with COVID, it has been horrific, a horrific scenario, this pandemic, with no end in sight, despite the vaccines and the mitigation efforts as this thing begins to morph in concerning ways. But we didn't, and hopefully we never lose 30 million people. We did some things right. And HPC was at the basis, HPC and AI, our ability to marshal the underlying technologies and the science and the rapid progression of vaccine development that really helped mitigate the dynamics of this pandemic. But there are some truths that exist. 50 million people died in 1918. It was a horrific pandemic. At the same time, the dynamic within pathogens that exist today is very, very concerning. Zoonotic diseases, which are those diseases that move from animal to human, once relatively rare, now are the dominant behavior of these pathogens, remain at very high risk. And of the 1,415 pathogens known to infect humans, 61% are zoonotic. I mean, humans are the dominant host that these pathogens will likely jump to. Things like combinatorial flus and drug-resistant superbugs and viruses such as Ebola and Zika are on the rise. I mean, these pathogens are aggressive. And as we know from the previous set of data, there are no borders, right? Infectious diseases don't respect borders. They diffuse into host populations so that they can replicate. And that's what they do really, really well. So the scenarios in front of us are concerning. And I think if we learned anything from COVID is that we need to be prepared and we need to think about our preparation in a different way. Risk mitigation demands a holistic strategy. And if you look across these dimensions of how we would build the right kind of resilient infrastructure with the right kind of scientific infrastructure and preparedness, okay, what would that mean? What would have to be true to make that true? We would be sequencing the genomes of these pathogens. We would understand potential vaccine candidates in advance in case of. We would build the right kind of surveillance infrastructure to do predictive modeling and identify through AI and HPC potential rogue or early signals that might signify something was happening in a remote place around the world. We would build these community mitigation measures around how you would contain diffusion early on in advance. We would have a better communication and public outreach infrastructure to mitigate false news and keep people up to date on what they needed to do on a global basis to sort of contain the diffusion of future pathogens. All of these things, if we were to do them not right, would mean that we would in advance leverage and take advantage of this extraordinary infrastructure, this computational and scientific infrastructure we have now, and build a front end, sort of get in front of future scenarios as opposed to respond to and react to, where you lose 3, 4, 5 months in advance as you build the capacity to understand the pathogen, the genome of the pathogen, potential vaccine and therapeutic targets, et cetera. So when I look at how we think in going forward of a global holistic strategy around public health, all of these things, many of these things, and most of these things actually really require the computational and scientific infrastructure we now realize we need, that we have at our disposal now to really kind of to have that resilience and capacity to react in a much more fundamental way. So at the inception of COVID, about 15 or so organizations came together and built what they called the HPC Consortia. AWS was one of those companies. Our peer, Microsoft Azure, Google Cloud, manufacturers, government agencies, universities, again, banded together and built this scientific and computational infrastructure so that the scientists, the vaccine developers, the people doing different scenario planning, et cetera, could have the capacity to compute on, a sort of a free capacity to build insight into what was going on with COVID and what were the potential mitigation strategies. And we learned a lot of stuff from that. AWS themselves had 17 projects that they were participating in and providing credits and infrastructure and scientific support. And we learned a lot of stuff from that. And it gave us some insight into what we could do next that might be that might help us marshal the resources and the capacity in advance as these things propagate out in the future potentially. We learned 3 important things. One was scale matters, right? Having the infrastructure to deploy the compute and AI resources at a moment's notice to compute on everything from genomes to genealogies to drug targets and therapies, et cetera, mattered a lot. And it significantly accelerated the work. We could not be where we are today with COVID without the scale and the capacity of this collection of HPC assets. The second is there is no silver bullet. These are very complex problems. They're multidimensional. They have deep interdependencies between climate and pathogens and human migratory patterns and all sorts of things that dynamically interact. That dynamically react. These things are very, very multidimensional and very complex. And so having the capacity to compute around all these different iterations and scenarios is critical, but there is no silver bullet. These things are very, very complex. And the last but not least is that we're really only scratching the surface of what's possible. And the consortia really demonstrated the commitment of a community of researchers, public sector leaders, and the community of infrastructure providers to test new ideas, to iterate with each other, to build a community and a resource and a capacity of shared knowledge and shared data to really, really tackle the challenge of COVID-19 head on. It was really just this extraordinary moment in time that just showed what is possible. So you have to look at, one of the things we learned in this notion of scale matters is what did the cloud actually enable research community, the scientific community, the response community to do? And, you have to begin to be able to ask yourself, could you reimagine how you can solve really hard problems if you could escape the bounds of on-premise? And we found that, as we all know, on-premise infrastructure, you have a fixed capacity, right? You can run models to a fixed size. And one of the things we really recognized in COVID is the enormous dynamic and opportunity to scale the problem set, to iterate on many, many more through stochastic models around possibilities, to expand the aperture of the number of drug targets, to expand the space of different chemical and biological compounds, to look at synthetic populations on how diffusion was likely to behave in different scenarios. And the cloud really helped the researchers and the scientists escape the bounds of where they were before. And it really massively compressed the time scale by which we were able to solve some of the most important problems related to COVID. And Moderna actually did its compute on AWS. And without going into all the problems, we know what the problem state was. The most important thing was what did having access to the AWS infrastructure enable Moderna to do? And it was able to design and ship the first clinical batch of its coronavirus vaccine in 42 days. Okay. And it was just absolutely extraordinary. They were able to, using AI algorithms and HPC, they were able to go from rapid experimentation to designing the mRNA drug and understand sort of the range of DNA sequences to control their analyses, etc. It was just an absolute extraordinary outcome of Moderna's ability to really rapidly accelerate their R&D and discovery process, getting to a therapeutic in 42 days. To me, that is the possibility of what cloud affords researchers and scientists and PIs and public sector and philanthropists to solve some of these hard problems that we face as a society. At AWS, one of the things this has led to is an organization that focuses explicitly on impact compute. How do we take what we know? How do we take the scale and the capacity? How do we take the scientists and the engineers and the people who are passionate about solving the hardest problems? And how do we put them to use on our platform? And, we're looking at a range of targets and how we marshal the resources around sustainability and conservation, around health and public health and disease mitigation, food security. Right now, we're in discussions with a whole range of people to reimagine what is possible using the infrastructure and the capacity that we have. But we're thinking about it differently. And if you look at the problems that have happened with philanthropic efforts to solve many, many of these problems in the past. It's the business design, the design of how you actually scale and sustain this has perhaps not met expectations for what is needed in the long haul. And so we're thinking very differently about how do we build communities around the capacity? How do we build engineered and referenced architectures to scale? How do we make sure that there is the capacity on an ongoing basis to support and sustain the economics, the business design of solving some of these hard problems? And so I am so passionate about this. It's one of the reasons I came to AWS is how do you think about scale, the scale that we can affect change? And I'm very, very, very proud of the work we're doing in the Impact Compute Group and excited about the outcomes that we're going to see going forward. So bringing this back now to how these things manifest and what it means to HPC and AI and their capacity to be a fundamental component of change with respect to these grand challenges facing humanity. One of the outcomes of the COVID HPC consortia is that it led a number of us to think differently about what were the learnings, and then how do we think about having some sort of a national strategic computing reserve, a stockpile, if you think about it, a strategic stockpile to do exactly as I talked about earlier around how do you think holistically about mitigation efforts, right? How do we accelerate our nation's ability to respond to events, whether they're pandemics, whether they're oil spills or wildfires or earthquakes? How do we have the computational and the scientific infrastructure that we're always in the ready, much like our military is in the ready? And we're deeply engaged in conversations with OSTP and our peer national security organizations to build the mechanisms to have flexible infrastructure, computational HPC capacity to support all of these problems to do the work in advance, to have the knowledge and the scientific readiness and have the computational capacity to be able to iterate and solve these hard problems at a moment's notice. And I'm very excited to be part of this initiative, for AWS to be part of this initiative. And we expect to have some sort of a strategy and outbound information not in the not too distant future. So let me conclude now with some final thoughts. The world is absolutely at a new set point in terms of the divide between the rich and poor expanding, and just the level, the scope, the scale of humanitarian crises are increasing. They're more complex, and they're escalating in terms of the exponential collateral impact they have on our planet. This is amplifying the global risk in terms of security risks and without a doubt, increasing global instability. I mean, the world is becoming a much less stable place. And the dynamics that sit underneath it, climate change, human migration, wars, displacement, food security or food insecurity, are increasing the global instability. The consequences are enormous. There's certainly a funding and commitment lag, and we feel that what has come out of COVID is perhaps a new way to think about the preparedness, the ability to marshal resources at a moment's notice, the ability to marshal a scientific community to focus on these really, really hard problems, and having access to the computational infrastructure through cloud and our public sector resources really puts us perhaps in a much more capable having more capable and more capacity on a going forward basis. But we really need to think differently and reimagine how we implement and scale these resources, making sure they are hooked into all the mechanisms to have the most scale and impact to the people who need it most. I want to thank all of you for your time. Go out and change the world and have an amazing day. Thank you so much.
Thank you, Deborah. That was really terrific. I'm really impressed by the scope of the vision. And one particular, this idea, those several things, some technical details that I was really fascinated by, like the Moderna, the use of AWS, that's very exciting. But then you were talking about this sort of national strategic computing reserve, which I think is really an interesting idea. And so a question I have is that how about are the national labs going to be part of that discussion? I would hope so. And how about the NSF? The NSF, my experience is kind of sometimes drags its feet on this sort of stuff. Any thoughts there or things you
I do. So Dennis, thank you for having me at this wonderful event. I really appreciate it. And I will take any opportunity to talk about, I think, the most important things that are happening around us that I can, which is outside of our general day-to-day in these bigger problems. As far as the MCSI, the National Computing Strategic Initiative, no, NSCI, sorry, National Strategic Computing Initiative, excuse me. Very much the national labs are part of this. You know, we have a working group and we have representatives from Tri-Labs and beyond who are thinking about this, recognizing that. So when you think about this problem statement, you have, and putting the NSF in the context of this, you have primary kind of discovery, and then you have readiness and execution, like the sort of being, having sort of the pre-work to be able to initiate, problem solving, when necessary. And we're trying to reconcile those two things, right? Because the NSF has been much more in the pre-work. Let's go study, right? Long longitudinal studies, primary research, if you will, on new areas that you need to be in the second state, but they're often at different timescales. So I think one of the things strategically we're trying to figure out within this NSCI is, where do we want to be, right? We have a whole scientific infrastructure that's doing really important research, but we need to make sure we have the capacity and the resilience to be like, again, the National Guard, the computing National Guard. So right now, the majority of effort in terms of partnerships are with the national labs, particularly the ones with the big infrastructure that will just be part of this resilient, elastic kind of capacity, and not yet so much the NSF infrastructure, if that makes sense.
Yeah, it does. Mm-hmm. As I said, I think the NSF tend to move slowly in some ways. So we have some other folks here online, and if any of them, hi, Bruce. Hi, Kyle. If anybody else wants to jump in with a question right now, that would be fine. Just make sure you unmute yourself to do so. Okay, everybody else is okay. We're going to return at the end of the session for more discussion. But right now, we're going to turn to our second speaker, which is Mr. Prabhat. And he is going to share his screen and start his presentation.
Sounds good. Can you hear me, Dennis?
Yeah.
All right, perfect. Just give me a second. All right, so first, let me just acknowledge that Deborah's talk was just wonderful. I think, it's a classic vision talk at a global scale. And I was just reflecting back on my career at Berkeley Lab and NERSC, wherein, I've given a lot of talks on AI for science and problems at the scale of the universe, all the way down to subatomic physics. Deborah mentioned climate change. I recently completed a PhD on applying AI techniques to problems in climate science, in particular, characterizing the impact of extreme events like the hurricanes that we've had recently. And I think one of the things that I found firsthand was that when it truly comes to applying AI techniques to large-scale science problems, you actually do need HPC resources. Independently, the godfathers of modern AI, as they've gone about training their language models and CAD detectors and so on, they've also reached the same conclusion in that AI is fundamentally an HPC problem. So I think just reflecting back on my time in the DOE, certainly, tried to push on the frontier of AI and HPC for science. And recently I moved to Microsoft Azure. I think realizing that perhaps the future of HPC and AI at scale is probably in the cloud. So this talk is going to be a technologist talk. So Deborah was at the 30,000 feet level talking about global scale problems. I'm going to jump down to maybe 100 feet level on what does it take to actually get AI jobs to run at scale, and what kind of platforms are being deployed right now on Azure to accomplish that vision. So sorry for the switch in context and scales, I guess. Let me just give you a quick outline for what I want to do in this talk. So I want to give you a very quick overview of high performance computing at Azure. I'll talk about a few products that are most relevant to this audience, which is the CPU-oriented and the GPU-oriented SKUs. I'll present some concrete results that we have on scaling simulation workloads and running some standard HPC and AI benchmarks. And then also have some thoughts on general trends, I guess. Let's see. All right. So first, just some standard slides, I guess. Azure, much like our partners at AWS and GCP, we have a global footprint. So there are several dozen data centers all over the world, which truly does allow for reliable services. Depending on which part of the world you're in, there might be some unique requirements around compliance, who can access your data, so on and so forth. So Azure has protocols in place for handling all of those requirements. There was a time when one thought about the web as a bunch of loosely coupled web servers that were perhaps not doing very interesting computations. It is now the case that when you look at a provider like Azure, you can find high performance computing resources all over the world, and you can find resources where you can actually run demanding AI workloads. So it's no longer the case that the cloud providers are offering loosely coupled computation. It is now the case that you can actually get access to high quality HPC resources. I want to share some of the latest results that we have in this talk. Now, having worked at an HPC center for a while, we know that it is not purely about the compute, and it is not necessarily just about coupling the compute with the fast network. So while, of course, we do this, we do have a number of CPU and GPU capabilities. We have codes now that run on tens to hundreds of thousands of cores, and AI jobs that run on thousands of GPUs at the moment. We use InfiniBand for connecting all of this compute on our HPC instances. Storage is important, so access to data, being able to share data is really quite key. So there are a range of HPC storage options that one can leverage in Azure. And then I think we all understand that for the kinds of complex scenarios that Deborah was mentioning, where you might have data sets coming in from a diverse set of sources, and you need to run complex workflows, orchestrating the movement of data, co-locating compute with storage, having automatic failovers, so on and so forth, is really quite important. So there are a number of services in place now where you can do all of that in Azure. Finally, of course, building on top of all of the substrate, you can have sophisticated AI machine learning models that, of course, once trained, can be deployed in practice in inference mode. So this is the set of VMs that we have on Azure. So again, I mentioned the classic loosely coupled computations such as web servers. You can have specialty SKUs in terms of supporting gaming, streaming, or analytics workloads, SKUs that support large databases, and other tasks that are I/O intensive. Now, we do, a couple of years ago, we announced a strategic partnership with Cray. So Cray is now HPE is the canonical HPC company. And on Azure, you have the possibility of leveraging Cray and HPE systems in the cloud. But really, I think when it comes to our HPC flavored SKUs, These are typically using InfiniBand. And then again, we have a bunch of CPU and GPU SKUs. I'll talk about those in a moment. And then we do have some FPGA specialty SKUs as well, which are oriented towards inference workloads. So for this audience, I believe that these two products are probably the most relevant. So if you have your classic simulation modeling workloads, then there are some Edge series SKUs that you can leverage. And then if you have state-of-the-art deep learning and AI workloads, then there are some GPU SKUs that you can leverage. I'm going to just go into a little more details now. So for what we call the HBV3 SKU, again, I'm sorry for the alphabet soup. I'm getting used to it myself. We have state-of-the-art AMD EPYC Milan CPUs, 2 sockets, 120 cores that your simulation workloads can use, plenty of memory, plenty of local disk, and the InfiniBand 200 gigabit per second interconnect. So we do, of course, hold back a few cores on some of the sockets for things that we need to do on the Azure side, but most of the cores are exposed to the simulation workload, so you can use that. And based on exactly how many cores your simulation workload might need, or rather how much memory they might need, there are variants of virtual machine configurations that you can leverage. For NDV4, and this is really the SKU that's probably the most relevant for AI at scale, we have the state-of-the-art AMD Rome processor, again, a 2-socket solution, 96 cores total, 900 gigs of memory, 8 A100 GPUs. So that's really quite a lot of computational horsepower on a single server. And then InfiniBand, of course, connecting different servers, but 8 InfiniBand cards on a per server basis. And again, plenty of local disk, which we found to be quite important for supporting both the metadata and data requirements for AI workloads. So again, just reflecting back to the DOE, again, I've always looked up to the national labs as a premier organization for simulation and AI workloads. If you compare server to server, the kinds of hardware that's in the DOE at the moment, if you look at Perlmutter, which is the latest system, and also Summit at Oak Ridge National Lab, really on a server-to-server basis, this design and this capability is really, really quite competitive. There might be some differences around the exact network that's used. There might be some differences on the I/O substrate, but from a raw computational horsepower perspective, it is no longer the case that hardware in the cloud is less capable in any way. So I think this for me really was the turning point wherein the conventional wisdom around leadership class supercomputing as being something that was the exclusive purview of the DOE or other, of course, international agencies. That's no longer the case. We have very capable hardware in the cloud, tightly coupled, that can support a range of demanding workloads. Now, of course, the story is not just all about hardware. I've actually worked on software and applications for most of my career, and really it is equally important to make sure that when demanding HPC or AI users come in, that they have access to optimized software stacks, and they can hopefully get a fairly high fraction of peak performance out of the box. So we do spend a lot of time, as do other cloud vendors, in curating images that have the right software stack configured and packaged up for your use. So things like IB drivers, IO middleware libraries, communication runtimes, the standard HPC libraries and BLAS and so on and so forth. Of course, your GPU drivers, any vendor-provided communication libraries are all now available. So if you are a simulation user, you'll likely exercise much of this stack. Similarly, for AI users, modern deep learning frameworks like PyTorch, TensorFlow are also packaged up and easily available. So just to share some numbers on how does simulation workload scaling look like at this point in time? So this is the HPV3 CPU SKU, and these are two more or less classic CFD applications that we tend to have a lot of customers of in Azure, and going anywhere from 1 to 64 nodes. On the y-axis is the speed up, and 1 to 128 nodes. We get reasonably good scaling efficiencies. So we are quite confident that for customers who have relatively modest scaling requirements, they can get fairly good fraction of peak performance and scaling efficiencies out of the box on HPV3. Now, obviously, communication is important. And when you talk about AI workloads, collective communication libraries like Nickel turn out to be really quite key. So these are just some lower level benchmarking numbers on the kinds of performance that you can expect for primitives like all reduce and all to all, as you vary message sizes from a few kilobytes all the way to several gigabytes, and on a range of concurrencies. So 16 participating MPI ranks all the way to 256. And in general, you can see that you can get reasonably good bandwidth on IB InfiniBand with Nickel. So touching up to 190 or so gigabytes a second is something that's doable for all reduces. For modern deep learning workloads, at least classical convolutional architectures and language models and so on and so forth, this is really the key primitive that is exercised when it comes to collecting all of the gradients from all of the participating processes. Now, all-to-all is a slightly more generic primitive. It's not exercised by typical deep learning workloads, but we are starting to see this being invoked by some very specialized AI workloads. Now, we have worked very closely with Mellanox in deploying something called SHARP, which is a hardware offload for accelerating several of these collective primitives. So again, AI, I think one of the advantages of modern AI really is that it's a very specialized workload. So it doesn't quite have the baggage of general purpose HPC. So when you look at reduced precision floating point standards and relatively simple operations like all reduce, many of those can be done in hardware. So that's something which Mellanox realized early on, and that's what they have developed the SHARP technology for. And that is something that we have now up and running on our dedicated NDV4 clusters, which is the A100 SKU. And using SHARP, again, you can go northwards of 200 gigabytes a second for the larger message sizes and get fairly good performance even for the intermediate message sizes. Similar results, I guess, around the scaling that you observe with and without SHARP. So again, you put all of that together. So compelling computational hardware on the server, InfiniBand as a compelling interconnect technology. You make sure that the software stack is fairly well optimized and accessible to users. And now you can run some standard benchmarks. Again, people tend to have varying opinions about the utility or relevance of HPL, but irrespective, it's been a useful benchmark to have in the field. And certainly, getting good performance or good numbers on HPL does require you to get a lot of things right. So while we don't build clusters necessarily to just run HPL, but as we deploy the clusters as a part of some of the validation work that we do occasionally run HPL and see how well we stack up. So this is an HPL run. On the x-axis are the number of the A100 NDV4 VMs that we are deploying. So 152 is what we went up to for this particular run. And then on the y-axis is performance in teraflops. So for this particular run, we get some fairly good scaling and get up to 15.3 petaflops. In particular, in the ISC timeframe earlier this year, after having run on 164 such VMs, we were able to demonstrate numbers going up to 16.59 petaflops. There's nothing sacrosanct about this particular concurrency. In fact, the clusters that we have for the NDV4 SKU are much larger than these. And some of the dedicated clusters that we are building from the NDV4 SKU are even larger. So nevertheless, this is what we had time for in this particular iteration of the top 500 list. And we were easily able to get up to the number 26 slot. Again, we don't particularly care about rankings on top 500 list, but just as an indication of the complexity and the scale of the systems that we are deploying, we decided to submit numbers this time around. Now, Jack Dogara and Horst Simon and Eric Stromeyer and others have been wondering about, augmenting the top 500 list with an AI benchmark or to have a separate, AI benchmark altogether. So there is a lower precision HPL AI benchmark now, and we did run those benchmarks on the same VMs. And, we got some fairly compelling 140 plus petaflop performance there as well. And while this the ranking and so on changes very quickly, but we believe that we were amongst the world's fastest 5 supercomputers at that point in time. So I think both from a simulation modeling perspective, but then also from an AI perspective, these platforms are really, really quite compelling. So I was talking about the benchmarking debate in somehow AI workloads are able to get away with low precision. So MLPerf is now a community that has been looking at both deep learning training and inference benchmarks for a range of different hardware. And we of course do ensure that we run some MLPerf benchmarks as a part of our validation process, and we get fairly good, strong scaling curves for the NDV4 VM as well. So I did want to call out this particular project called our strategic collaboration with OpenAI. So that's one of the reasons why I am at Azure. Like Deborah, I mean, I care a lot about the end use of HPC and AI. And in my mind, OpenAI is one of the leading entities that is truly pushing the frontier of what general purpose AI might look like, what kinds of architectures we might need to develop, and how we might need to deploy those architectures or train those architectures on leadership class systems. So Microsoft has, for the past few years, again, been working with OpenAI to truly advance the state of the art in artificial intelligence. There are a number of applications that have been called out around natural language understanding, some applications in computer vision, and really many, many other applications. One of the things that is publicly known about OpenAI is really the GPT-3 model, which a few years ago was being trained at the level of 175 billion parameters. Internal projects at Microsoft and other researchers in the community are now certainly way beyond that. But really, I think what I wanted to call out is that training a state-of-the-art NLP model like GPT-3 truly does require what we in the DOE would have called a leadership class HPC platform. And much of the work that we've been doing with OpenAI is exactly in that spirit, getting their contemporary and also next generation models running on some of these the hardware that I mentioned today. So this is a really exciting collaboration that we have with OpenAI. So so I just want to give a few concluding thoughts. Supercomputing in the cloud is real. The machines that we have, the performance that we're getting from them, the scale that they're running, that we're running the workloads at, is in all ways, I think, matches the classic definition of supercomputing. So in many ways, we believe that HPC is now democratized, and unlike, say, a classic on-prem HPC center where once you deploy a system, you're pretty much stuck with it for the next 3 or 4 years. You can have access to bleeding edge hardware more frequently than that. So every year there's a compelling CPU or a GPU or an FPGA SKU that comes along, and you can access that at a much rapid cadence than you would do with an on-prem solution. Deborah mentioned, this issue, of course, of elasticity, and as your workload demands, you can scale up or scale down as needed. That, of course, goes without saying is a unique value proposition for supercomputing in the cloud. The word leadership class supercomputing, I think, was exclusively used, I would say, in the Department of Energy and other international agencies. We're there now. It's not a pipe dream that'll materialize a few years from now. We're there now. And some of the numbers that have now been submitted to top 500 and Graph 500 are indicative of where we are. Finally, as I mentioned, initially Andrew Ng, I think, was the person who said that deep learning is an HPC problem, and I think that's been independently verified by many other folks subsequently. And I think the announcements that you're seeing from Tesla around the Dojo supercomputer and other efforts are really, I think, an independent validation of this statement that if you want to get state-of-the-art deep learning models running at scale, then you really do need an HPC platform. Now, this is really the reason why HPC, which might have been once secondary or tertiary activity in the cloud, is becoming a little more mainstream, because AI is, the growth of AI it just continues to go faster and faster, and there just seems to be no let up in terms of the sizes of models that people want to train or the amount of data they want to throw at the AI model. So really, I think what was considered to be niche at some point has become more mainstream. So that's a really exciting development, I think, for us in the cloud. So I did want to just call out that, we'll provide the slide deck to you, but there are a number of, if any of this sounds interesting to you and you want to give the products that we have on Azure a shot, there are a bunch of documentation and pointers here that you can refer to. We are hiring, so please, feel free to drop me a note if you're interested in positions in high-performance computing or AI at scale. And I'm going to stop at that. So thanks, Dennis, for this opportunity.
There, I'm unmuted now. Thank you very much for that. So I noticed there were there was a couple of questions that came across. Actually, Bruce, are you still there? Do you want to actually ask your question directly?
Sure. Yeah. Thanks so much for the very interesting talk, Prabhat. I enjoyed it. So one of your earlier slides, I thought you had mentioned the NDV4 instance for visualization, but I was wondering about that because I think that is using the A100, which, just like AMD has removed rendering pipeline support from their higher end GPUs. NVIDIA, I think, has done the same. So did I read that wrong, or was it more of a generic statement?
Yeah, so so there's certainly a diversification in NVIDIA's GPU portfolio, in that some GPUs are now exclusively for visualization, others are for more demanding AI workloads. As you might imagine, doing general purpose computation on GPUs, there are cases where you might need FP32 or FP64, but for AI, investing in chip area for lower precision arithmetic like FP8 or even lower makes sense. So yeah, so back to the question. Yes, A100, the SKUs that we put out are definitely targeted for AI training, and there is a different SKU that we have for visualization or rendering.
Right. Yeah, this is one of the areas that I'm interested in, because as you know, often these HPC or HPC plus AI workflows, at the end of the day, there's a visualization component.
Mm-hmm.
And do you do this offline, which is what's traditionally been done, or can this be in situ, which is I just don't know how often in situ visualization is. So that was kind of the motivation question.
Yeah, that's a good point. So there are a few modalities I guess I might imagine. You might have an inference oriented application. So perhaps you have simulation that's running, it produces a bunch of data, and now all you got to do is to render it, because, say in the classic exascale machines, we knew that we couldn't drain the data out to disk and then do the post-processing. So sure, so while the data is in memory, then you do in situ visualization, you use a graphics card that might be a little more viz-oriented on the node, render the image and then save the image. So that's certainly one modality. Now, mixing AI with the simulation, now that's where things get interesting. So if you have a classical CFD solver code running on a CPU, and perhaps you want to augment, do super resolution or do something else with, say, a deep learning model running in inference mode on a GPU, then that's an interesting prompt to go after. I suspect, so again, this is something which, I think the applied math community has not reached a conclusion on when you end up coupling classical PD solver with an enhancement or an augmentation via a deep learning model, what sort of resolutions, what sort of precisions are actually compatible? It's a different story to make a classification decision on, this class versus that class versus predicting a continuous valued field. So it's not clear to me right now on whether FP16 or FP8 will suffice for that, or we will need to go to FP32 or FP64.
Right.
So I think that might constrain the kinds of GPU, I guess, you might choose to co-locate on your server.
Yeah, very good.
Sure, thank you.
So Prabhat, I have a couple of questions.
Mm-hmm.
One is that have you guys, I think Microsoft may have done something with looking at some of the, I'm actually more interested in your own opinion of this. There's a lot of companies out there that are building very highly parallel, massive chips like GraphCore and some of these others that are not necessarily aimed at the training market, but for the deep learning net, but really for the the evaluation of the network. I forget what. Anyway, have you thought about that, or are you guys looking at that at all?
Yeah, certainly. I think all cloud vendors are, looking at custom hardware for both training and inference. NVIDIA has the leading market share.
Yeah.
And so I think it's good to have a few other options. Yes, so GraphCore is something that we've looked at in the past, and we continue to look at other options. So again, I think once we determine that some options are competitive in terms of price performance or power, then we will choose to deploy them as needed. But I will call that the software ecosystem maturity, I think, is a big concern, because I think that is really one of the genuine strengths that NVIDIA has and others perhaps don't. So, if there are users who come in and they want to get a better price performance or a power envelope or what have you, but they're just not willing to take the hit in terms of software maturity. So for a piece of code that was working great on the NVIDIA software stack, if that doesn't quite work on another solution, that turns out to be a big concern. So yeah, so I think the general answer is yes, that we are looking at options.
So I have another question, but maybe I'll save that till later, because I think it might be a good time to get Dayan up and running. How does that sound? Dayan, are you still with us here?
I am here. I'm here, Dennis.
Okay, great. So
thank you.
I'll let you do the share screen.
Thank you. And thanks, Prabhat, for a very good talk, because I haven't asked many questions, because in some way, I know Azure to a level, very good way. So you'll see in the talk. Okay, Dennis, tell me when I could start. I believe you can see my screen.
Yes, go ahead.
Okay, thanks, Dennis. Thank you for this opportunity. It's a great pleasure to be here. So I'm Jayan Thiagalingam, I'm head of the Scientific Machine Learning Group at the Rutherford Appalachian Laboratory. For those of you who don't know, Rutherford Application Laboratory is one of the national labs in the UK, sort of an equivalent to one of the DOE labs in the US, where our focus is very much on very core part of science. In today's talk, what I'm going to talk to you about is benchmarking for AI for science in the cloud. I'll cover quite a lot of terminology here just to make sure that you all are clear about what I'm really talking about. So for AI for science for us is basically using AI technologies for advancing science. That's a basic top level premise. But then if you drill a bit deeper, so for us, AI is anything that can actually make things in one way intelligent or the other. So including signal processing techniques or deep learning techniques or conventional machine learning techniques or Bayesian techniques. We kind of classify all of them as, for us, as AI. It could be quite religious, but we are not really religious people. We want to solve problems, so we tend to group them together as an AI technique. And the other part of the story is basically, we want to spend our time understanding the scientific data sets that basically underpins our science. And then by understanding that, we want to really advance the fundamental science. That's the overarching drive. And then, of course, the science here basically covers a very broad remit, including material sciences, environmental sciences, particle physics, astronomy, and life sciences. So these are the different areas that the Rutherford Application Laboratory works. And our group is very much in the center of it, working with these people. So we have people in the group with various different domain expertise, machine learning, signal processing, so on and so forth. So you can sort of gauge what AI for science literally involves. And then the question is why we have to really worry about AI for science. And of course, scientific data generated by experimental facilities such as ESRF or SSRF or Rutherford Application Laboratory or APS really growing in size very rapidly. So in fact, the notion of exascale is not just about the computing, but it's also about the data. Now, we have seen what AI could really do in various different areas of branches of technology. And, of course, science is not an exception. So we can technically use AI actually to kind of advance science. And this is where it comes as a cross-section of AI for science. How do we use AI for advancing science? And then why benchmarking then really matters to AI for science? Benchmarking conventionally being about, understanding the system performance or trying to gauge how different two techniques really work together. That's a sort of a focus we have been taught from our university days. But when it comes to AI, it has a slightly different spin. We're going to see that in a few minutes. But the first thing is, I think the ML doesn't have to be black magic. I think for most of I think probably if you are coming from a computer science background, this is quite a clear goal. We know what you're doing to a certain extent. There are lots of dark areas where we don't know much about machine learning, but to a certain extent, we are reasonably well informed. But even with that large amount of information, we still struggle to make an informed decision about what model would be a good thing or what system would be useful for a given scientific problem or how that would really work on our different data sets. So this level of understanding still lacks. And to make matters worse, I think there are lots of things going on. So for example, we have far too many machine learning models around. There are far too many scientific problems. If you were to really even take 10 problems per domain, you have lots of problems to kind of target. And of course, not to mention different type of data sets and different scientific facilities, and also different type of architectures. If you really combine all of them together, it becomes quite a difficult area to kind of manipulate, to knowing which techniques really work on which platforms across different data sets. So this is where the AI benchmarking could really make a bit of a difference, because through AI benchmarking, we'll be in a position to at least make some informed decisions about what is really possible and what is not really possible. And this is not really quite an easy thing to do, because we have lots of problems to work on. And then sort of a sensible current agenda is basically, going around each and every different domains and identify problems that are worthy of solving using machine learning. Because if you talk to scientists, they want to really apply AI. They don't want to know whether it's really possible or not. So in a scoping exercise, we want to understand problems that are really worthy of solving using machine learning. And then, of course, we have to see whether the problem actually relies on a very large scale open data sets, because we are very much interested about open science. This is our drive. And of course, the important thing is for benchmarking, we need to have a reference implementation. What is the reference implementation we are talking about? Now, with the reference implementation, I think there's a very important outcome out of this. So for example, here, very, very simple graph. It's nothing really from our work. It's just basically from one of the machine learning work packages. So this is simply about the performance of different clustering techniques and how that really works on data sets, across different data sets. You could see here, I think, some of the techniques really work incredibly well and some of them really perform miserably bad. So one of the techniques, you had to mark them as a baseline. So for example, that's my baseline technique against which I'm going to compare things. So this is where the conventional benchmarking comes. But then there are lots of other benefits out of the benchmarking as well. So particularly on the AI side of it, we want to really know whether we can actually use it for testing and bug fixing, or can we actually use it as part of the verification and validation workflow, or even part of a continuous integration one. But the important one is really is about what difference does it really make to science. I think if you were to kind of go around peer performance, then it's about comparing bare metal performance. But if you were to compare how two different techniques really work, that really is a totally different thing, because it could effectively come back to us with different advancements for different sciences. So because we have different baselines, so for example, if I'm talking about a denoising data set, so for example, that is a benchmark, I'll talk about it a bit later. So given a data set, we want to develop different AI-based denoising techniques. So if I were to come up with one, the community can really compete against it and come against with a better one. So for example, this is a basis of Kaggle competitions you could really see around. So in some way, this increases the openness and fosters the scientific research. So for us, I think the benchmarking has two different goals. One is actually the performance benchmarking, which is all about comparing bare metal performance or how different things really work. But the other side of the coin for us is really about science benchmarking. Have we got a better technique to do or achieve a certain type of problem? So the notion of a benchmark is slightly different for us. We basically combine a data set and a reference implementation together. That's the benchmark for us. So typical benchmark on a HPC domain is possibly about a loop or something very micro specific, whereas here we are talking at the application level and nothing really at the micro level. And these are some different benchmarks we have put together in the last round. One is basically about understanding the protein interfaces. So it's all about comparing different techniques for understanding the protein interfaces. Or here's a cloud masking one. This is about understanding can we actually segment cloud pixels from the satellite images? How two different techniques compare against each other in terms of doing that. And these have real life impact on how we do science. And this is basically about the one that you see, the one that you see here is about how cells really migrate at the embryogenesis stage. Or the last one is a very simple denoising. It's electron microscope data, and we want to compare 10 different ways of really denoising it. And these are very sample of different type of benchmarks, but we have about roughly 50 different benchmarks in our pipeline. So when we can do this across different domains, and if you can combine different type of problems, we can actually bring them together as a nice benchmark suite. So with that one, we can hack two different types of problem. One is we can really go away and understand the performance of different AI systems or bare metal performance. And the second one is, can we understand science better or the data sets better? But then there are lots of challenges in here. So for example, we have to go away and then think about how do we really bring up a platform to do these comparisons better, and about how do we distribute these data sets, because these data sets are not really small. I think the days of really working on 1 terabyte or 2 terabyte data sets is long gone. Our typical data sets are roughly about 50 to 100 terabytes. How do we move these around? It's quite a very difficult exercise. And the other thing is, there are lots of things going around. You have lots of different frameworks, PyTorch, TensorFlow, Scikit, and so on and so forth. You have hundreds of machine learning models, and you have lots of different architectures I talked about. How do we kind of get our head around? And the last one is, how do you evaluate your benchmarks? What is the real metric? In one way, in the old days, it's just purely about megaflops, how many floating point operations you can do per second. But now, all of a sudden, this is about science. So should we really talk about, so for example, if you're denoising, it's a decibels or signal to noise ratio. Or if you're really counting cells, it's counting. If you're talking about the protein docking, it's a slightly different metric. So all of a sudden, our metric of benchmarking really changed as well. Now, so this is the basic definition of where the benchmarks are. And to say where we are with the benchmarks. So there are not many scientific machine learning benchmarks around. There are 2 of them at least. There are 2 key initiatives. One is ours, of course. This is called Scientific Machine Learning Benchmarks. So this is with STFC, Oak Ridge National Labs, and Indiana University with Jeffrey, but he moved to Virginia now. You can find that code. And the other one is very much on the ML Common Science Working Group. There are 2 different goals. One is the second one is very much industry focused. It's about industries trying to compare different things at different scientific problems, whereas we are very much interested about the openness of the science, and we are interested about reproducibility. We are very keen on knowing can we advance science, whereas the second one is about vendors competing against each other to kind of make their systems better and better. So that's a current state. And to kind of make it more contextual, I talked about one of the key problems about distributing large data sets. So the problem for us now is we can't simply say, okay, you go and download a data set here. We can't do that because the benchmarks have 2 parts, data and the code. Code is easy. We can easily say, okay, get it from GitHub. We can get away with it. But the data is quite a notorious part of it. So what we have done for that one is, this is the sort of a technique that is being adapted by ML Commons and all other collaborators we have. Effectively, the data is basically put into an object storage and also in remote mirrors. And when you run a benchmark, that particular data set is downloaded on demand, because it might be not possible to download everything in one go, because all of them could be about 1 petabyte in size. So you might want to download the benchmarks and data sets that are directly relevant to you. Now, there are lots of issues here. So for example, if you're running behind the DOE machines, you may not be able to do this because you may have an internet connection. But then, of course, you can download it and move it around. So this is the state we are in. Okay, now let's really talk about how this really fits in the cloud and why do we have to really worry about cloud at all. Now, of course, there are lots of benefits of really running these benchmarks on cloud. I think a variety of hardware resources. I think if I were to go away and then buy all these different types of machines, it becomes almost impossible. I can't really convince my lab to do this. And then the other thing is, even if different people have different machines, it's a difficult thing to kind of compare apple versus orange, because, so for example, the graph core system we have might be totally different to what others may have. So different configuration, different interconnect, all sorts of things. Whereas if you have it in the cloud, it's a very nice one place. We can actually do a very fair comparison of specification. Regardless of the algorithmic or alphabet soup that Prabhat was talking about, it's very difficult to get our heads around systems. So this is one of the important things. And also, it's very difficult and very easy to get very large scale infrastructures, which is very difficult in a national lab, let alone in any other organization. The procurement time basically drags forever and we can't get anything done. And of course, you can have all sorts of things. You can have mixed settings, and those are really ideal settings for us. And then the other important thing is, of course, I have really pulled 2 different images from the Azure and AWS here. So effectively, data in the cloud, because we have, this is a very important advantage. The problem is moving around large data sets is quite a notorious thing to do. Whereas if we can run our benchmarks from the cloud, we don't have to do that. The data sets could be there forever. And then users can simply plug into these ones, they can run it and they can move on. But of course, this comes with all of the restrictions. I'll talk about it in the next few slides. So for example, if you were to talk about a cryo-EM data sets, if every user has to download 50 terabytes, it's quite a long time to do it. Whereas if you can keep it on the cloud, they can get the machine they want, they can actually run it, they can move on. And the other important part of this one is we can also really, I think both Azure and AWS have lots of, and other cloud platforms have very powerful ETL pipelines and ingestion workflows. Typically, you can get the data sets from the facilities and you can actually sort of build a real nice workflow which can really automatically handle all this for us. And the favorite of this one is basically doing inference. I'll cover that in the next slide. So there are 2 things now so far I have talked about. One is variety of hardware resources and the data in the cloud. And then, of course, the main important thing is about ease of developing AI applications, because these benchmarks basically give a blueprint for scientists what they can do on different types of problems. What they can do is easily they can clone it, they can actually develop it. And all these different platforms really give a very important, very serious capability in terms of really developing things. So for example, you can have collaborative notebooks, we haven't seen that before. I think this is very nice. And also all cloud platforms have very good ML tools. You can have labeling and you can have very complex workflows and absolutely stunning APIs and services. And my favorite of this one is Inference Services. The facilities can actually don't have to do any inferencing at the end. They can simply call the API and done, which is a very nice thing. And of course, basically copy pasted one of the images here. You have different perspective of what you want to do on the machine learning front. I think the development is one of the nicest thing on the cloud. And then, of course, there's open science I talked about. Now, if you can really do all that on the cloud, which is very nice, you can have everything in there. There are lots of models and all of the users can actually share things. And it's a very fair comparison against every single platform you could think of. Sure, there are lots of caveats around publication and dissemination. Scientists do not want to share immediately, but at least over time, things can become a lot easier. But then these are not really without challenges. I think the first one is to say the least is basically the security part of it. Sure, there are lots of things goes around, but the difficulty is around convincing scientists that the data sets are secure in one way or the other, particularly around the publication side of it. They're very nervous of it. I'm not a security expert, so I'm going to skip this one. But the second major sticking point for us is basically the cost of it. Now, effectively, if you want to run data and compute and services, it's really going to cost us money. And compute, we could really sort of manage in one way or the other, but keeping very large data sets in the cloud is not really an easy thing to do. It's not really cheap either. So this is a very small study we have done ages ago with Linda Sheridan and Max Raju in the UK. We were kind of trying to scale where our data sets are really going. So we were assuming, okay, we'll do 200 gigabytes in the first quarter, the second, and also believe that we had to keep all these data sets over time. So we thought, okay, let's test 30 terabytes in the third quarter of the 2021. So this is basically per quarter, we had to spend about $2,000 to keep those data sets. And these costs are without any bells and whistles. These are basically very simple ones. There are no interest charges or anything, just plain storage. So you can see that cost very easily, ramp up very easily. 30 terabytes is literally nothing for us. One little benchmark has about 50 terabytes easily. So you can imagine the amount of cost that really shoots up. There are ways around it. There are ways around it. We could go about Azure Open Data Set, so open data in the AWS, but then there are lots of limitations around it. It's sort of a one-way street. You can put in there, but then after that, okay, you can't really modify things. Whereas on the benchmarking domain, we want to make sure that it's not really about purely distributing data sets. It's about having a very healthy discussion, a very healthy competition, a very healthy comparison of things. So as such, these two routes do not quite work out. We spend a fair amount of time understanding this, how to do this, but in the end, we sort of ruled out that may not really work out for us. And of course, the concerns of portability, that's a major thing for us. I think scientists are very, very specific about wanting to run their code wherever they want. The issue is, I think, depending on how we develop our benchmarks are very open. We don't particularly use any Azure-specific services. But of course, over time, people might really prefer that for ease of use because they might prefer drag and drop and they could want to do that. Whereas that could actually have a long-term effects as well. The applications might become very locked to one particular platform and might simply prevent us from running somewhere else. And of course, the portal complexity, not to mention the alphabet soup that Prabhat was talking about. There are lots of things, and getting around any of the cloud platform GUIs or the browser windows is not really easy. We are faint-hearted, but even if you're brave, it's just quite tricky. And not to mention about forgetting to shut down your VM and having a surprise build. And the very important thing is the vendor support. I think the issue is running benchmarks in the cloud is a very nervous thing because vendors may not be very keen on reporting their results, particularly if they're not very configured correctly or if they're not very optimally configured. Sure, it really leads to a better opportunity for these systems to be configured nicely, but scientists can, if they are not well informed, they can report any sort of number. So that could be a bit of a nervous point for most of the vendors. And we had discussions in the past, and we were told, I think in some way the preference is not to report these numbers very openly. So to kind of conclude it, I think so AI benchmarking is quite a useful for understanding the machine learning and AI. It has a lot of potential to kind of advance science. And sure, we can do benchmarking on our systems, on our on-prem systems. You can download these benchmarks, data sets, and we can run these. And we can, of course, share those results. But then, over time, we can compare things. But having it in a central place, like in a cloud, could be really, really transformative. And it could really lead to a lot of good things. But these things are not without really challenges. There are lots of things in there, and there are lots of things that we have to address. So currently we are working on a version called SIML Bench Cloud, which is purely about taking the SIML Bench into the cloud, trying to see what the options around, and we are exploring lots of different possibilities in there. But the difficulty is basically not just the cost side of it, but we need a lot of support from the cloud providers if that has to take off. It's not purely about the cost, but it's about the portability, platform support, and vendor openness, and all sorts of things. So with that one, I will stop, Dennis. If there are questions, I'll be very happy to take. Once again, thank you all, and thanks, Dennis, for inviting me.
Okay. Very good. Thank you very much. That was fascinating. So I notice we have a question, and this is Bruce again. Yes. Why don't you go ahead and ask it?
Sure. Thanks, Dennis. Benchmarking, I've always found it to be kind of a tricky, a tricky exercise, right? I mean, anytime we've had to, bid on for national lab systems, there's always a set of applications or micro benchmarks or whatever that we need to project performance on. And what I've noticed is, how you compile these applications, what compiler you use, what compiler options, that in itself can impact the measured performance. And then, as you also pointed out, the data sets that you use, the size of the data sets, et cetera. And then when you start adding all these accelerators and, GPUs now, but also FPGAs and graph core and, some of the other accelerators, I think that complicates things more. And a lot of these independent hardware vendors, produce their own reference versions that are actually optimized for their platform. And I was wondering how you manage all that.
Okay, good question, Bruce. I think you just sort of a very, very much of a shooting on my forehead. That's a very good question as well. I think in some way, I think you have to answer in several stages. One is, I think this is what our focus is slightly different, because we are purely focusing on the science side of it. So we particularly didn't really right at the beginning, we didn't really care about the runtimes. We were relying on Python frameworks, and each of these frameworks are very subjective, and it's also subjective to how do you write your code, because I could write a better PyTorch code than someone else, and my TensorFlow code is really, really not that good. So all those things could easily kick in. So what we are doing now is there are two ways that we are kind of trying to handle this. On the science side of it, we are purely on the Python side of it, which is relatively easy for us to handle. But the real difficulty is basically on the system side of it, because as you said, what compiler we are using, even using Python may not be sensible, because if you're looking at, sort of a second level, or not to mention microsecond, but, second level performance, a sub-second level performance, Python is possibly the wrong language to use at that point. So one particular thing we are looking into now is basically working at the back end of the frameworks. Now, all these TensorFlow and PyTorch have a C++ implementation. We are working with them. And we also have a sort of a hardware software co-design program as well. We are trying to work with them, because I think at some point I was a compiler person, but I moved on, and I don't really optimize code anymore. But optimization could take ages. So we are working with vendors actually to do this. So for example, in one of the benchmarks, the release, we are working with NVIDIA to do that, and equally we are working with Graph Code to do that for us, to come up with a much optimized versions of it. Sure, it is still subjective. So this is why one of the key things we are after is even the baselines may not be what we call a concrete baselines. They might change over time. You might really come up with the same baseline in a much better implementation. And if that's the case, the ground would move, and then we have to say that's a new baseline. So probably, does it really answer your question, Bruce, to a certain extent? I'm sure that
you definitely answered my question. It's I mean, I think it's tricky and it's a moving target, and it gets complicated, and it'll get more complicated as there's more AI acceleration hardware out there, I would think. So yeah.
Oh, thanks, Bruce. Thank you.
Thanks.
If I may, Dennis, could I ask a question? Or?
Yeah, go ahead.
Gian, I was wondering, a while ago, as we were thinking of, so Jeffrey Fox was, part of the MLPerf discussions, and we were thinking about the challenges in creating a MLPerf benchmark for a scientific application. And I think, when we were discussing this with the traditional HPC folks, the issue of reproducibility became quite important. So as you run the same benchmark on many more compute nodes, or as you run the benchmark on a larger data set, you should hopefully get the same answer. So if you're training a neural network, for example, like you should get an equivalent neural network that gives you the same predictive accuracy for whatever task you care about. And it became really quite difficult to think through, I guess, all of the issues in how do you assure that beyond just initializing the neural network, how can you make sure that the stochastic gradient descent would operate at least functionally in the same way? So I guess I'm just wondering, to the extent that you're choosing to train neural networks as part of your AI benchmark suite, is guaranteeing or assuring equivalent predictive accuracy, irrespective of what scale or dataset size you train the neural network on, is that a consideration, or have you?
It is.
Mm-hmm.
It is, Prabhat. I'm sure that you're familiar with the ML comment sort of setting. We are trying to mimic something similar. We want to really do that in two different ways. One is, I think for science side of it, scientists don't care how many machines you run. They particularly care about the results. So for them, I think it's absolutely crucial. They don't want to know how many nodes we ran. They want to know, am I getting the right answer? Whereas on the performance side, it's a totally different stuff. So for that one, what we are trying to do now is basically we are trying to create two different branches of it. One is to say very close setting. There are lots of restrictions of what you can do with it and what you can't do with it. So for example, this is the way you have to initialize your networks. These are the things that you have to do. Even with that one, I think we are really having lots of difficulties to kind of guarantee that level of convergence or accuracy. And the other one is very open, because we don't particularly care what you do, but come back. But of course, it's up to the scientists to say this is good or bad. Because the worry is our original accuracy may not be even good enough in the first place. So even that's a moving target. So this is definitely in a serious consideration. And it comes into the reproducibility covers two sides of it. One is basically the benchmarking is one, definitely. And also the second part is so very much on the large scale data sets as well, because our one really works amazingly nice when you train and you do the inference, it's nice. The inference reproducibility is a very hard thing to track, because as soon as you throw something else, you get totally different performance results, totally different science results. And that is a very much of a nervous point for scientists. And this is one of the difficulties to convince scientists to kind of accept it. Sure. They're like, it has its own mind, but it's actually producing. And the third one is basically on the AI HPC conversion side of it. This is about the, when you start to use surrogate models and things, maintaining the ab initio accuracies is a very, very difficult thing, because, machines do different things and your accuracy might drift over time. So there are three corners we are fighting this, and these are not easy things, I have to say, but definitely we thought about it.
Sure, thank you.
Thank you very much, all of you. Actually, we have exactly, less than 1 minute in our time, and they're very strict about the time in these events. This was all recorded, and I'm going to, when the recording is available and public, I'll send around a note to all of you so that you can notify all of your friends and colleagues where they can come and listen to the full thing. This is a great session. I really appreciate your help on it. I still had more questions, and I guess I'll have to figure out how to ask them individually. So thank you all very much.
Thanks, Dennis.
Thank you, Dennis. Thanks, Prabhat. Thank you, Bruce. Thank you all. Bye.
Bye.